One of the key problems in quantum mechanics and in quantum optics is the decoherence problem. How to understand decoherence, and specifically how to understand quantum aspect of the decoherence, is central to this lecture. What we're going to see is briefly the description of something called as pure state. We will define in terms of quantum mechanical description what do you mean by pure state, what is the value of looking at such state, and we'll now introduce an element of environment into this particular problem and ask what happens to the pure state when it comes and encounters the so-called environment. Then we will look at the concept of something called as tracing, which means that the mixture between the pure state and the environment has some interesting effect, and that is the point which will help us to understand the concept of the so-called decoherence problem. Finally, we will look at this classical limit and try to understand decoherence from a perspective where one takes some particular interaction and extrapolates it to classical limit. How does it look like, and what is the prescription to define such a kind of a problem? Let's start with the so-called the pure quantum state. To begin with, consider a quantum system in a superposition of two states, and we can define that by this function psi, which is now represented in the form of ket. And here is the superposition. It has two states, 0 and 1, and associated coefficients alpha and beta. Now, if you have such a kind of a state, the state is represented by something called as density matrix, rho in this particular case. This density matrix is now defined by this Ket and Bra description, where the psi is again coming from this particular function, what is already been defined. If you take this density matrix, you now have the alpha modulo alpha squares and modulo beta squares as cross diagonal elements, and off diagonal elements is now the product of these coefficients with their conjugates, and this is an important off diagonal element, and you will see why it is so. The probabilities of being in the state 0 and 1 are essentially determined by the so-called diagonal terms, as we already discussed. And the off-diagonal elements, as I mentioned, is the important aspect of the so-called coherences. They also represent something called as interference terms, because depending upon how these terms kind of interact, you would end up getting a coherent or a decoherent kind of a system. And this is where the interference aspect of the mixing of states comes into picture. Now let's look at the interaction with the environment itself. As you know, there is absolutely no quantum system which is perfectly isolated. Uh, as long as it is in a particular state, it would always be having some kind of an external environment which is interacting with it. That interaction, it can be represented by this vector E, or in this particular case, the bracket kind of notation E, and this leads to something called as an entanglement. And this entanglement is with respect to the state what we have defined, and this particular environmental state what is now being defined. And that entanglement is now represented by the psi total, and the psi total essentially is alpha times the 0 state times the E naught state, and plus the beta, the 1 state number 1, and also the E1 state. And E1 and E naught essentially comes from the environment, which is resulting because of the interaction with the state 0 and state 1. If you look at the concept further, we can now ask the question, what happens to this interaction? Since the environment is too complex to track, we use something called as a reduced density matrix. And this is the formalism which is usually represented by something called as tracing out the environment. In such a situation, you essentially have this reduced density matrix represented by a trace of this particular density matrix, what we have already defined. And this yields a particular system density matrix, which is represented by the cross terms. And now this is where the interesting thing comes into picture with respect to the interaction between the system and the environment. The off diagonal elements, which are essentially the representations of the coherences, are now represented by not only these products, but also there is a product with respect to the E0 and E1 states and E1 and E0 states. And this particular interaction is what makes the problem interesting and also in a way kind of challenging, because the term Eij, where I is just the kind of index what is representing 0 and 1, represents the overlap or similarity of the environmental states. So if these two specific states are essentially the same, then this product turns out to be 1. However, if they are orthogonal to each other, this product goes to 0. Now is the interesting aspect. The classical limit emerges in the context of the macroscopic world when the environment states become orthogonal almost instantaneously. Okay, which means that this particular overlap, what we have been defining, tends to 0, which means that this product tends to 0, which means the off diagonal element which we defined in the previous case would actually vanish. And therefore, the matrix becomes diagonal in nature, and this is the representation of the decohered state represented in the density matrix formalism. The modulo alpha square and modulo beta square essentially are representing the cross terms, and these cross terms essentially the diagonal terms, and these diagonal terms represent a kind of a state where there is 0 on the off diagonal elements. The result, what you end up getting, is that the system no longer shows any kind of interference effects. It behaves like a classical probability mixture and therefore represents a decoherent state. In that sense, what we have now looked at is a emergence of this particular classical limit, starting with the pure state, then we introduce the environment, then we mixed the environment and the pure state, and finally we ended up with the classical limit. And this classical limit is what is something very fascinating, because this is the decoherence concept which is so vital in so many applications, because the decoherence is the reason why you end up actually getting your devices in the quantum kind of technology to behave in certain way which is very close to the classical technology. If you want to retain the quantumness of that particular system, you have to somehow kind of avoid this particular decoherent state, which means that you have to delay that particular relaxation of the system from a coherent to the decoherent kind of a situation, and that itself is a very interesting challenge. But what we have discussed now is essentially kind of an overview of the decoherence kind of problem, and the decoherence essentially is because of an interaction between a system and an environment, and that interaction is what is leading to this particular aspect of decoherence, and has deep implication in understanding quantum mechanics and also utility in quantum technologies, including quantum optical technologies.